An unusually powerful earthquake has once again drawn global attention to southern Italy, striking directly within one of Earth's most closely monitored volcanic regions. Why did this particular earthquake command immediate international attention, even though its magnitude was not among the world's largest? Why are scientists paying such close attention to every new tremor beneath Campi Flegrei? At what point does a powerful earthquake become more than an isolated seismic event and begin raising concerns about changes occurring inside an active volcanic system? Those concerns intensified following a magnitude 4.5 earthquake that struck near Quarto on the evening of July 31st, sending residents rushing outdoors, damaging buildings, disrupting transportation, and extending an earthquake sequence that has already reshaped daily life around the Bay of Naples. According to the United States Geological Survey, the earthquake occurred at approximately 17 hours, 46 minutes, and 43 seconds Coordinated Universal Time. Its epicenter was located about 1 kilometer, or roughly 0.6 of a mile, north of Quarto, Italy, at a depth of approximately 5 kilometers, or about 3.1 miles. Although a magnitude 4.5 earthquake may appear moderate when compared with the devastating earthquakes that occasionally exceed magnitude 7 or even magnitude 8 around the world, its location made it exceptionally significant. Instead of occurring deep beneath a major tectonic fault far from population centers, this earthquake originated directly within the Campi Flegrei volcanic caldera, one of the most densely populated active volcanic regions on Earth. The distinction matters enormously because earthquakes inside Campi Flegrei are rarely viewed as isolated tectonic events. Every tremor becomes another piece of evidence, helping scientists understand what is occurring beneath the caldera. Each earthquake provides clues about stresses building inside the crust, the movement of underground fluids, and the continual deformation affecting one of Europe's most complex volcanic systems. While most of these earthquakes do not indicate that an eruption is imminent, their frequency, depth, location, and magnitude are carefully analyzed because they reflect changes taking place within a volcanic environment that has remained restless for many years. Residents across the Naples metropolitan area felt the shaking almost immediately. Reports described buildings vibrating, furniture moving, and frightened families leaving homes, offices, and public buildings as the earthquake rippled across the region. The shaking was strong enough to interrupt transportation, temporarily affect electrical service in some areas, and produce visible structural damage to older buildings already weakened by repeated seismic activity over recent years. Emergency responders quickly began assessing damaged structures, while authorities carried out inspections to determine whether buildings remained safe for occupancy. Aftershocks followed, reinforcing fears among residents already accustomed to living with persistent seismic unrest. Unlike many earthquake-prone regions where months may pass without noticeable activity, Campi Flegrei has experienced an extraordinary increase in seismicity during the past several years. Swarms involving hundreds or even thousands of earthquakes have become increasingly common. Many individual earthquakes have been relatively small, often too weak to cause damage, yet together they reveal a pattern of continuing unrest that scientists cannot ignore. Each new swarm demonstrates that stresses continue accumulating within the crust as the volcanic system slowly changes shape. Campi Flegrei itself is unlike the familiar cone-shaped volcanoes that dominate postcards and travel brochures. Visitors expecting a towering volcanic peak similar to Mount Vesuvius are often surprised to discover that the supervolcano appears more like a broad landscape filled with towns, neighborhoods, roads, parks, and ancient ruins than a single mountain. The caldera stretches roughly 12 kilometers, or about 7.5 miles, across, encompassing densely populated communities west of Naples. Millions of people either live within or immediately adjacent to this enormous volcanic depression, making it one of the highest-risk volcanic regions anywhere on the planet. Its appearance reflects a remarkable geological history. Rather than being constructed by repeated lava flows building a mountain over time, Campi Flegrei formed after colossal eruptions emptied vast underground magma reservoirs. Once enough magma had been expelled, the overlying rock collapsed inward, creating an immense basin surrounded by fractured crust. Later volcanic activity produced dozens of smaller craters, lava domes, vents, and fumaroles scattered across the caldera floor. Instead of concentrating volcanic activity at one summit, the system became distributed across numerous potential eruption sites. That characteristic makes monitoring especially challenging. Future volcanic activity, should it occur, may not necessarily emerge from an existing crater. Instead, new fractures could develop where underground pressure finds the path of least resistance. Scientists therefore monitor deformation across the entire caldera rather than focusing on a single volcanic vent. Sophisticated networks of seismometers, satellite observations, global navigation satellite system receivers, gas monitoring stations, and ground deformation measurements work continuously to detect even subtle changes occurring beneath the surface. Among the most closely watched indicators is a process known as bradyseism, a term describing slow uplift or subsidence of the land over periods ranging from months to decades. Campi Flegrei has experienced repeated cycles of rising and falling ground throughout recorded history. Entire harbours have alternately risen above sea level and later subsided beneath it. Ancient Roman structures preserve striking evidence of these movements, with marine organisms leaving unmistakable marks on columns that spent centuries partially submerged before the land eventually rose again. The present period of unrest began attracting increasing attention during the early years of the 21st century, but accelerated significantly over the past decade. Measurements revealed that portions of the caldera were rising at rates considerably faster than previously observed. Neighborhoods around Pozzuoli became focal points because repeated surveys documented continuing uplift affecting roads, buildings, pipelines, and other infrastructure. Although the vertical movement may appear modest when measured over days or weeks, its cumulative effect becomes substantial over years. Ground uplift occurs because pressure within the volcanic system changes over time. Scientists continue examining the relative contributions of magma movement, hot fluids, volcanic gases, and hydrothermal processes. One widely discussed interpretation suggests that magma remaining several kilometers beneath the surface releases heat and gases into overlying hydrothermal reservoirs. Those fluids expand, circulate through fractures, and increase pressure within surrounding rock. Another possibility involves magma itself slowly intruding into higher levels of the crust. Regardless of the exact balance between these mechanisms, the resulting increase in pressure gradually deforms the overlying ground while generating earthquakes as rocks fracture under stress. The relationship between uplift and earthquakes is particularly important. Rock behaves elastically only up to a certain limit. As underground pressure increases, the surrounding crust initially bends slightly. Eventually, accumulated stress exceeds the strength of local faults or fractured rock, producing earthquakes that release part of the stored energy. Rather than reducing concern entirely, those earthquakes often indicate that deformation remains active because the crust continues adjusting to changing underground conditions. For decades, Campi Flegrei experienced relatively quiet intervals punctuated by occasional periods of increased unrest. During the early 1980s, however, a dramatic episode of bradyseism lifted parts of Pozzuoli by nearly 2 meters, or approximately 6 feet and 7 inches. Thousands of residents were temporarily evacuated because authorities feared volcanic activity might follow. Ultimately, no eruption occurred, and the crisis gradually subsided, demonstrating that significant unrest does not always culminate in magma reaching the surface. Even so, the episode fundamentally changed the scientific approach to monitoring the caldera. Since that time, technological advances have transformed scientists' ability to observe the volcano. Modern satellite radar can detect ground movements measuring only a few millimeters. Dense seismic networks record tiny earthquakes previously impossible to detect. Continuous gas monitoring measures changes in emissions from fumaroles, while sophisticated geochemical analyses examine variations in underground fluids. Together, these tools provide an unprecedented picture of the volcanic system's evolving behavior. Even with these advances, Campi Flegrei remains exceptionally difficult to interpret because volcanoes do not always behave according to simple patterns. Ground uplift can accelerate and later slow without leading to an eruption. Earthquake swarms may intensify before declining again. Gas emissions sometimes increase because hydrothermal systems reorganize rather than because fresh magma is rapidly ascending. Consequently, scientists evaluate numerous indicators simultaneously instead of relying on any single measurement. That complexity explains why the magnitude 4.5 earthquake immediately attracted worldwide attention. Its significance extends well beyond the number assigned on the magnitude scale. Stronger earthquakes occurring within Campi Flegrei indicate that stresses inside the crust continue evolving. They also test infrastructure repeatedly exposed to months and years of smaller tremors. Buildings weakened by repeated shaking may become increasingly vulnerable, even if each individual earthquake remains below the threshold associated with catastrophic structural failure. Another reason this earthquake stands out is its position within a broader pattern rather than as an isolated event. Campi Flegrei has experienced repeated earthquake swarms throughout the current unrest episode, with seismic activity reaching levels unprecedented in modern instrumental records. The continuing occurrence of larger earthquakes suggests that the crust is responding to persistent pressure changes instead of returning to a stable equilibrium. Every additional earthquake, therefore, contributes another chapter to an ongoing sequence that scientists continue studying with exceptional care. Attention quickly shifted from the immediate effects of the earthquake to a far more consequential question. Why has Campi Flegrei begun producing progressively stronger earthquakes after years dominated by smaller tremors? The answer lies not in a single fault or one isolated pocket of magma, but in the gradual accumulation of stress throughout an enormous volcanic system that continues to deform beneath one of Europe's most densely populated urban regions. Unlike tectonic earthquakes generated primarily by the movement of massive crustal plates, many earthquakes inside Campi Flegrei are directly connected to the volcano's ongoing unrest. As pressure increases within the caldera, rocks that have already been weakened by thousands of years of volcanic activity begin to fracture. Every fracture releases energy in the form of seismic waves. A single earthquake may relieve stress along one crack while simultaneously transferring additional stress to neighboring fractures, sometimes triggering clusters of aftershocks or entirely new earthquake swarms. That process has become increasingly evident during the present phase of bradyseism. Measurements collected over recent years show that portions of the caldera have continued to rise as underground pressure steadily increases. While the annual rate of uplift has fluctuated, the long-term trend remains unmistakable. Roads have required repeated maintenance. Buildings have developed new cracks. Underground utilities have experienced additional strain as the land surface slowly changes shape. None of these changes occurs overnight, yet together they reveal a volcanic system that remains highly dynamic rather than dormant. The magnitude 4.5 earthquake that struck near Quarto therefore represented far more than another point on a seismic map. It became one of the strongest earthquakes recorded during the current period of unrest and demonstrated that the crust is capable of releasing larger amounts of accumulated stress than many of the smaller events that have characterized recent earthquake swarms. For local residents, that distinction carries immediate practical consequences because stronger shaking substantially increases the likelihood of structural damage, especially in older masonry buildings that were never designed to withstand repeated seismic loading. Even moderate earthquakes can have cumulative effects. A wall that survives dozens of smaller earthquakes without visible damage may gradually lose strength as tiny fractures develop within bricks, mortar, and supporting beams. Another stronger earthquake can then enlarge those hidden weaknesses into major cracks or partial collapses. Engineers often describe this as progressive structural degradation, where repeated shaking slowly reduces a building's ability to resist future earthquakes. Within historic cities surrounding Naples, where many buildings date back decades or even centuries, that issue has become a growing concern during the prolonged bradyseismic crisis. Infrastructure faces similar challenges. Bridges, tunnels, water pipelines, electrical networks, rail systems, and underground utilities all respond differently to repeated deformation of the ground. Slow uplift changes the relative positions of foundations over time, while earthquakes introduce sudden accelerations that stress joints, supports, and buried connections. Although modern engineering standards greatly improve resilience, infrastructure originally constructed long before current seismic design practices may require continual inspection as unrest persists. These realities explain why scientists and emergency planners pay close attention whenever earthquake magnitudes begin approaching the upper range observed during volcanic unrest. Every increase in magnitude represents a substantial increase in released energy. Because the earthquake magnitude scale is logarithmic rather than linear, each whole number increase corresponds to approximately 32 times more released energy. Even a half-step increase represents several times more energy than the previous event. Consequently, the difference between a magnitude 4.5 earthquake and a magnitude 5.5 earthquake is far greater than the numbers alone might suggest. That brings renewed attention to one of the most important questions surrounding Campi Flegrei. Why would a magnitude 5 or larger earthquake be especially dangerous even if no eruption occurred? The answer begins with the extraordinary concentration of people living inside the caldera. Millions of residents occupy communities built directly above an active volcanic system. Many neighborhoods contain narrow streets lined with older residential buildings, historic churches, schools, hospitals, commercial districts, and transportation corridors. A stronger earthquake affecting such an urban environment has the potential to produce consequences extending well beyond the immediate epicentral area. Ground shaking generally increases with earthquake magnitude, but the local geology around Campi Flegrei can further amplify those effects. Portions of the caldera consist of relatively loose volcanic deposits, ash, pumice, and sediments that respond differently from solid bedrock. Seismic waves passing through these softer materials may become amplified, causing stronger shaking at the surface than would occur over more competent rock. This phenomenon helps explain why earthquakes of moderate magnitude sometimes produce unexpectedly intense local effects within volcanic regions. A magnitude 5 or larger earthquake could therefore generate significantly stronger accelerations across populated communities surrounding Pozzuoli, Quarto, Bacoli, and western Naples. Older masonry structures would face greater stress. Buildings already weakened by repeated earthquakes might experience partial failures. Falling masonry, collapsing chimneys, damaged facades, and broken infrastructure could present immediate hazards even if the earthquake itself remained relatively modest compared with major tectonic disasters elsewhere in the world. Another important concern involves the condition of the crust itself. Years of uplift have gradually stretched and fractured portions of the caldera. Each new earthquake modifies that network of fractures. A stronger event may create additional pathways, allowing volcanic gases and hydrothermal fluids to migrate more efficiently through the subsurface. While that does not automatically indicate magma is moving toward the surface, changes in underground permeability can alter gas emissions, hydrothermal circulation, and pressure distribution across the volcanic system. Scientists therefore examine every larger earthquake for evidence that the internal plumbing of the caldera may have changed. One widespread misunderstanding deserves careful clarification. A magnitude 5 earthquake does not trigger a volcanic eruption simply because it exceeds a particular numerical threshold. Volcanoes do not operate according to fixed earthquake limits. Instead, Eruptions occur only when magma ascends sufficiently toward the surface and the surrounding rocks can no longer contain the internal pressure. Earthquakes may accompany that process, but they are only one component among many indicators scientists evaluate. For Campi Flegrei, researchers continuously analyze earthquake locations, depths, ground deformation, volcanic gas chemistry, temperature changes, and satellite observations together, rather than relying upon seismicity alone. If earthquake activity increases while uplift accelerates, gas emissions change composition, and evidence emerges that magma is migrating upward, concern would naturally increase. If only one indicator changes while others remain relatively stable, the interpretation may be very different. As of the first day of August in the year 2026, monitoring agencies continued reporting that Campi Flegrei remained in a state of significant unrest, but without definitive evidence that an eruption was imminent. The earthquake sequence associated with the magnitude 4.5 event produced numerous aftershocks, while emergency inspections continued across affected communities. Authorities maintained heightened surveillance of the caldera through one of the world's most sophisticated volcanic monitoring networks, reflecting the reality that although the latest earthquake underscored the volcano's continuing activity, forecasting the precise evolution of such a complex system remains one of the greatest challenges in modern volcanology.